So we spoke about expanders, and the last thing we said is that the expander inequality is independent of the power, which in practice, I mean for us, because we just proved something for the real line with power 2, it just means that we can go from L2 to L3, but I didn't touch upon the subject of what happens with the expander inequality in other Banach spaces. Is it true, is it not true? And this is genuinely a huge open problem, basically. So I'm not gonna get to that at all. But the short answer is we don't know, but there's a lot of things that we would like to know about expanders with respect to Banach. Now I'm going to move to the other graphs that I mentioned in the morning, and because I don't just want to deal with embeddability into L2, because for L2, I mean there are fairly simple proofs of everything I'm going to say. So I want to deal with embeddability in more general Banach spaces. I'm going to need some facts about Banach spaces. So for applications, you can just think of LP with, I'll explain where LP comes into play, but I just want to isolate the important properties. So I'll start by speaking about uniform smoothness and convexity, which are two very important properties of norms that have been studied for a century. I will use a formalism that's somewhat more recent. It's due to, and of course equivalent up to constant to what people were doing earlier, but this is due to both Carden and Lieb, I think 93. So, so a space X is P uniformly smooth. So P uniformly smooth if there exists a constant S such that for every X and 1 in X, the following all equals true. So if I take the average of the norm of X to the P plus the norm of X to the P, this is bound above by the norm to the P of the midpoint plus a constant to the P times the Pth norm of the difference. Okay, Pth power of the difference. Okay, and here, sorry, I should add that P is a number between 1 and 2. I'm going to comment on this in a second. And it's called Q uniformly convex if, again, there exists a constant which I denote by K now, such that for any 2 points, I have the following equality. So I will start with this side now. So it has the norm of the midpoint to the Q plus 1 over the constant to the Q times the norm of the difference is bound above the average of the difference. Okay. And here again I should add that Q is a number between 2 and infinity. The interpretation for Q times infinity is the obvious one. You take the 1 over Q power and so much. Okay, and the least constants are denoted by the P smoothness constant as T of X in K2X. So from now on, whenever I P smoothness to convexity, I mean this constant. Okay, these are all kind of notions of convexity of a space. So by convexity of the norm to any power greater than 1 is a convex function. So if you want, this says that this convexity can somehow be reversed up to an additive error. Whereas here, it says that this convexity, which appears that this is smaller than that, can actually be improved. So you have a little bit of a benefit. Okay. And where is this all coming from? It's coming from the fact that if you have Hilbert space or the real line, and you put exponent 2 and constant equal to 1, this is an identity, right? So this is the parallelogram identity. So these are meant to be two one-sided relaxations of the parallelogram identity in opposite directions. Okay? And if you want, I can give you a little exercise, which it's an exercise. It's a version of something that was already proven by Lindenstrauss in the 60s, I think, is that if you take 1 over p plus 1 over q to be 1, so conjugate exponents, so the p smoothness constant of the dual space is equal to the q convexity constant of x, and the q convexity constant of the dual space is the p smoothness constant of x. Okay, so the fact that there's iterated duality is okay. It's something that follows from other principles, that this implies that also, but okay. So x double star is finite representative of x for those who know. But okay, so there's a perfect duality between the constants, okay? So if you compute this, then you can compute, yeah.
Is it true that, for example, usual LQ is like that?
No, we'll get to that. Okay. We won't compute, but this is the definition. Okay, so this is the definition of smoothness and convexity. And okay, I mean, here the thing that you can check is that when p becomes larger in the smoothness inequality, the inequality becomes better. Okay, so when p is larger, the inequality is better. So it cannot be better than 2, which is what you would get for the real line. And conversely, when q becomes smaller in the goes for smoothness, when q becomes smaller in the convexity inequality, again it becomes better. So it cannot be better than 2, which is what you have for the real line. Okay, so this is the limitation. Okay. So, to answer such a question, so we want to compute these things at least from some reasonable spaces. There's a 2-point inequality somehow, 4-point, depending on how you look at it. So, for LP spaces, this has been done. Again, the formulation at the time was slightly different, but morally this is due to Clarkson in 36. Again, not up to the constants that I'm going to state. But it says that if p is a number between 1 and 2, L1 is not uniformly convex, it's not uniformly smooth, nothing like that, it's strictly convex even. LP is p smooth with constant 1 and 2 convex are always being uniformly with 2 convexity constant, which is 1 over square root of p minus 1. And let me just write it, even though it's followed by duality. If q is between 2 and infinity, then q is 2 smooth with 2 smoothness constant square root of q minus 1 and q convex with q convexity constant. Okay. This is not a completely different square root of p minus 1, but the square root of p minus 1 in Bonami's level. So yeah. Not a great thing. I mean, there's a proof of this using Bonami's level, so among other things. Now, these are very classical facts. I thought of proving them in the past when I gave a similar main course. I proved them, but maybe for this course it's better to move on to some other things. But these are 2-point inequalities about functions in LP. Okay, so it follows from Bonami's lemma and Hanner's inequality, basically. For those of you who know what Hanner's inequality is. Maybe I should say a remark, which again, this is a theorem first due to Tomjak in the late 60s or in the 70s, but finally due to Borchardt and Gottlieb. So the same moduli, so the same constant for the Schutting classes. So if rather than LP you look at matrices with certain P norms, same inequalities are satisfied, of course more complicated proofs, but exactly the same with the same constants and everything. And very nice open problems related to that. So Hanner's inequality for matrices was only proven last year in the last range that was missing. So anyway, so the message that I want to convey is that these are invariants which in principle we can compute for some reasonable spaces. Okay, so it's just checking 2-point conditions. But 2-point conditions, I mean, in principle, they're not very good to yield nonembeddability in any way, right? This is a very isometric criterion of whether this inequality is satisfied or not. If you deform a norm by a factor, it will stop being valid. And this is where a bit of probability is going to come into play. So we'll speak about martingales Banach spaces.
Sorry, so the definition of this P unismooth and P uniform reduced and Q uniform convex were given in 1993.
This definition. There is an equivalent definition.
So this term was stated in a different language or?
There is a different quantity that was called the modulus of uniform convexity and uniform smoothness, and if this was bounded from below or from above by a corresponding power, then this was what they called B uniform convexity at the time. The two definitions are equivalent up to the value of the constants. Okay, so the constant one, the constant the other, the constant S is something different. But this is a bit more useful for iteration, as I'm going to show in a bit. So yeah, up to this theorem was proven in the 30s up to the value of the constants. So, any more? Okay, so now we're going to see how we're going to iterate these properties. This is by introducing martingales. If you want sort of a concise introduction on the subject, Thomas has a 2,000-page book, which is going to be longer soon, so you can start there. Okay, so for these lectures, here's what the martingale is going to be. Okay, so it's going to be something very specific. So let X be a arm space. So an X valued martingale is a sequence of functions, a finite sequence of functions. So everything is going to be very finite. So mk. So the kth function is going to be defined from the k-dimensional Hamilton with values in x. K goes from 0 to n. Finite but arbitrarily long. So it's a sequence of functions satisfying for every k between 0 and n minus 1, and for every x1 up to xk in minus 1, 1 to the k. If I want to compute the value of the k function at the point x1 up to xk, so the k function depends on k coin flips. Okay, so this is going to be the average of the k plus first function with respect to flipping the last coin. Okay, so this is going to be mk plus 1 at x1 xk comma 1 plus mk plus 1 at x1 xk comma minus 1, and I will divide by 2. Okay, so I am gonna allow myself to call martingales, to call Pelley-Walsh martingales general martingales, which is not in general true, of course. There can be a very complicated filtration, but for the geometric purposes that we discussed, it's all completely equivalent. So there's some argument in the 70s and the 80s by Moray, Padilla, and others. Having these geometric properties for general martingales is equivalent to just studying this very, very simple martingale. Okay? So for our purposes, it's all going to be the same. And so here's a remark, which does the definition make sense? So here's a remark, which you probably will know. If X is the real line, or a Hilbert space for that matter, sorry, I should say M0, I defined as a function minus from 1 to the 0, is just a constant function. Okay? If X is the real line and you want to compute the difference, the second moment of Mn minus M0, M0 is just the expectation, what this is just a sum of squares of the increment, right? So martingale differences are orthogonal. So this is just a sum k goes from 1 to n of the expectation and k minus and k minus 1 squared. Okay, so martingale differences are orthogonal. Of course, this is a very scalar fact. Why on earth would we? Yes.
The x1 all the way to xk are elements of -1, 1.
Yes. Thank you. Yeah. Thanks a lot. So martingale differences are orthogonal. And of course, this is a very scalar fact. They give you a norm, no reason to expect that something like this happened. Here you expand the square. But here's the definition which Didier gave in 75. So a norm space has, on the one hand, martingale type P, which is suggestively a number between 1 and 2, if for every x valued martingale, is if I should say here, there exists a constant, a positive constant t, such that for every x valued martingale, the pth moment of Mn minus M0, where now I measure the difference in this norm, is bound above by t to the p times some k goes from 1 to n expectation mk minus mk plus 1 to the p, and it has martingale cotype q, where now q is of course bigger than 2. Okay. If there is a different constant c such that for every x valued martingale, we have a converse inequality with power 2. Right? I'm going to put the constant denominator here to indicate that the constant will always run above it from above. Okay. The same way as smoothness and convexity were designed to be one-sided relaxations of the parallelogram identity, martingale type and cotype were designed to be one-sided relaxations of the orthogonality of martingale differences. Shouldn't have to read that. Any questions on definitions?
So Hilbert spaces have type and cotype too.
Yes. Hilbert space have type 2. Hilbert spaces are characterized by the fact that they have type and cotype true, even up to constant, I mean. Yes. So, and the big theorem in this field, or I would say in this theory that I'm discussing now, is something that's called PTS renorming theorem. From that same paper, so 75. And he showed that the Banach space nurtured has martingale type P or cotype 2 if and only if n x admits an equivalent P uniformly smooth or convex in the case of cotype. And it's called the renorming theorem because the difficult part, of course, is you assume that, I should say, okay, I shouldn't rush. So these properties are isomorphism invariants. So you take a norm, you replace it with an equivalent norm, but up to a factor of 10, this only affects the constant. In the definition of smoothness and convexity, this is no longer true because the constant appeared in only one of the summands. So one of the two is a very isometric property, whereas these are clearly isomorphism invariants. Okay, and Pizia said that if you want to study the classes of P smooth and Q convex spaces up to isomorphism, what you end up is really marking the type and cotype. Okay? So, so this is called the renorming theorem because the difficult part, or the more difficult part, is to start with this property of martingales and come up with the equivalent P smooth or Q convex norm. So of course we're going to prove the other one. So, and actually for the case of the other one, the case of cotype is a bit more difficult, so we're going to do it in the bigger one. So proof, just to give you an idea of how these properties are iterated. So proof of easy direction for type. Okay, so assume that your space is P smooth basically. So for every x and y, let me remind you, x to the p plus y to the p over 2 is bound above x plus y over 2 to the p plus this universal constant, which doesn't depend on anything, is x minus y over 2 to the p. So this is an assumption from now on, and let mk an x valued martingale. And I mean, the inequalities I want are translation invariant, so let me, without much generality, assume that m0, which is just the expectation, is signature. So let's prove this has to be there. It's not difficult. So I wanna, my left-hand side is the expectation of mn to the p. So this is an expectation over n points of the hypercube, right? So I write it as an expectation over n minus 1 points, and then an expectation over the last coordinate, and here I'm going to have mn for the first point, and then xn. So what this is, it's an expectation over x bar of, here I'm going to have an average, I'm just going to expand what this expectation over 2 points means. Mn x bar comma 1 to the p plus mn x bar comma minus 1 to the p divided by 2. Okay, so I just wrote what the last expectation is, and now let me just apply the assumption. That's x to the p plus y to the p over 2. So first, I'm going to have the expectation over x bar of the midpoint. So it's gonna be mn x bar comma 1 plus mn x bar comma minus 1 of 2 with p plus then the constant and the expectation of the difference. Okay, so we didn't do anything, I'm just plugging in the inequality. Now what is this?
-1.
Okay. So this is -1. We're ready to iterate, and now we need to look at what this is. So let me just draw a picture. So here I have mn x bar comma 1. Here I'm going to have mn x bar comma minus 1. And what I have is half the distance between these two. Now what is the midpoint again? The midpoint is mn minus 1. So both this distance, so half of this distance is either that or that. So this is just mn minus mn minus 1. So this is the first increment, and I am one step behind, so I just iterate. So you do it again, you get mn minus 2 plus the second increment and so on. So you really iterate the inequality directly, and you get a property for x value martingales with this vanilla definition of a martingale. Okay. Any questions about this?
So this is 75. This is before the definition of the inequality.
Yeah, with the other equivalent definition. It
So
was.
the original argument is a bit more.
Yes, exactly. There is some more credit to be given to the. Okay, happy to give all the credit, but yeah, there is some. It was a bit more complicated, but morally this kind of iteration.
Why is it more difficult for cotype? Isn't it just exactly the same?
Second. Yeah. But if you want to do it for general martingales, there's one additional sort of Jensen inequality somewhere, I think, which might become tricky. But again, not really. But I think you are right. Yeah. Well, it is right. Yeah. Thank you.
And in the difficult direction, you just start with x in Banach space and consider all martingales.
Exactly. Yeah. So you need to define what the norm at the point is, and you find all possible martingales that start at that point and have a certain property, and then you need to discuss it. Yeah, but you need to show that something is a norm, and that something is not obvious that it's a norm. But yeah. So it's a very clever proof. But yeah. So you define it taking into account all the inequalities. Any more questions? Okay. So this allows us, using the extraction theorem, to compute the martingale type and cotype of all LP spaces. Okay, and everything we're getting here is shown within this.
Stupid question. Any relation with the linear type?
I'm getting. So Mark. It's a bit like we staged it, but so here's a very simple example of the martingale. I should have mentioned that. So a family of functions of the form nk of x, which is a sum I goes from 1 to k xi vi, where vi are some vectors in my Banach space, is a martingale. So martingale type implies that for every n vectors in the Banach space, if I look at the fifth moment of the Rademacher sum, xi vi is bound above by some constant e to the p the P, and cotype Q implies that this, the Qth moment for Rademacher sum, is bounded below by 1 over c to the Q times sum di to the Q. This is a very special case of a very special martingale that's in fact a sum of independent random variables. Very special. Now these properties have names. These properties are called Rademacher and cotype. The properties for which in the opposite a lot, you understand and get that there are one level of complexity below with just about sums of independent random variables rather than general martingales. So it is in various cases easier to check that they are true. But this was a question at the time that this theory was developing of how different the two properties are. So how different the Rademacher properties are from their martingale analogs. Okay, and let me just mention two results. So for instance, if one wants to check the Rademacher type and cotype of LP spaces, this is simply a consequence of the Kinchin inequality. So one doesn't need to go through the Clarkson proof and prove this complicated two-point inequalities. So it's just a consequence of Kinchin's inequality, and Kinchin's inequality, even though, depending on how you like to prove it, it might not be clear in the beginning, but it also works for p equals 1. Okay, so of course everything's clear in 2024, but okay, so just a remark. So L1 has Rademacher cotype 2, in fact, so the best possible cotype, but no martingale cotype. Okay, so here's a very simple space for which the cotype versions are different. Best possible space. Okay, good enough. For type, actually, that's not the same. Okay. So there exist examples of spaces which are distinguished, but it was an open problem that PCA asked, and that's solved. So there exist spaces of different, put it that way, martingale and Rademacher. So in the literature, there are 3 examples of spaces like that. Okay, so whole bunch of space literature, I know of 3 examples. So Pizier, 36, then James, 78, and Pizier shooting. So I don't know more, but these are the examples I know in the literature. Okay, so in principle, going from martingale to Rademacher type, in theory, it's very good. In practice, I mean, the examples are few, but there are good theoretical reasons to do it. Of course, but it's from what we know now, it's exotic Banach spaces which are between the two categories. But this doesn't mean that we don't care actually. Okay, so these were the preliminaries from Banach space theory. Are there any questions? Okay. So let's move on. Let's go back to embeddings, and I promised you that the next thing that we're going to do is Hamming graphs. And the invariant now that we're going to have is metric versions of type. Okay. So Hamming graphs and metric type. See. And let me start with directly with the definition. Okay? Maybe if you want a simple exercise. So if a space X, a Banach space, has Rademacher type P greater than 1, then any linear operator T from L1n, this is my definition for Rn with the L1 norm, into X satisfies that the operator norm of T and the operator norm of its inverse is bounded below by n to the 1 minus 1 over 2. So this product of operator norms here is meant to capture how good an embedding T is. Okay? And the theorem, this observation really, I mean, it's a straightforward application of the condition there, tells you that if your space has non-trivial Rademacher type, then you cannot embed well the n-dimensional L1 space into your Banach space. But this is about linear embeddings, okay? And our goal is to deal with nonlinear embeddings. So for this, we're going to give a definition that n flooding in 69, not with that terminology, but okay, so metric space MD has n phenotype P, which is now just a positive number, if, so previously the condition was that for every n and for every n vectors in my space, something holds. Now the statement is that for every n and for absolutely every function from the hypercube into X, we have an inequality. Sorry, I should say again, if there exists a positive constant such that the following holds. We have an inequality, so I look at the expected distance in my metric space between f at a point and f at some pixel. I raise it to power p. This is bound above by t to the p and the sum as k goes from 1 to n, expectation over x of the distance in the metric space at f at the point x1, f at the point x minus and f at the point where you flip the k coordinate. Okay, so if this property is valid for any function with values in a metric space now, I say that the space has n flow type. Okay. And fine is the definition, so let me make two remarks. So first remark, if the metric space turns out to be a Banach space, so if it's a linear space, I can choose f to be a linear function. Okay. So if f of x is a sum of xi di, I deduce that n flow type clearly implies Rademacher. Okay, so it implies Rademacher type clearly with the same constant, but at the same time I should insist this is a property which I can define for a metric space. There's no linear structure assumed. And I want to make a second remark. Very good. Now, this also, just to remind you the first lecture, so there was this dual formulation of bi-Lipschitz embeddings. I was taking distance between points with some probability measure on the left, distance between points with some probability measure on the right. This is of this form. Now, on the left, the measure is uniformly random 1 point, deterministically it's antipodal, and here it's a sum over edges, and then a uniform point, and you flip the case edge. Okay, so the second remark is that if n has n flow type p, then the bi-Lipschitz distortion of the Hamming cube, I should, I just write dh to indicate the Hamming distance, right? dh is the L1 distance of the Hamming cube. Into M is bounded from below by n to the 1 minus 1 over 2. Okay, I can redo this computation, but it's the same computation we've done twice already. I mean, these points here are at distance 1, so I sum it up, I get n. These points are at distance n, so I get n to the p, so the two sides are not matching. So I have to pay by the distortion, right? So n cotype serves as an invariant to embeddings of the hypercube in the sense that we're exactly discussing this morning. Any questions? But so far, okay, it's a perfectly nice invariant. Can we actually compute it? Okay, and the answer for Banach space we can't fully know, but I won't get to that quite yet. I want to show you the first theorem that someone proved for that, presumably without this terminology, with the theorem that Christoph proved in '96. Was this during your PhD or?
Shortly before.
Shortly before? Okay. I didn't expect that. Okay, which I was very proud to be the first person to cite it in 2023. So somehow this had been unnoticed even by people exactly in the community. Like there were famous papers later that reproved similar things. So Christoph proved that a space, a norm space, with martingale type P has an M flow type. Okay, so if you have a norm space, then M flow implies Rademacher. But if you assume the slightly stronger assumption of martingale, slightly okay, depending on historically slightly in the sense that there are many examples, then you can actually prove M flow type. And the proof is not going to be exactly the way it was written in Christopher's paper, but in a way, the moment you know this one what you want to prove, there's only one way to prove it. So let's do this proof. Okay? Any questions about this thing? Okay, so I need to prove this inequality, right? So let f from the hypercube into x. I need to prove this thing about f, and I'm going to consider a martingale. Which one? There's only one. Right? So consider mk of x1 up to xk to be the expectation over yk plus 1 up to yn of f x1 xk yk plus 1 up to yn, which is an x-valued martingale. The rest can be almost left as an exercise, but let's do it. Okay. Now would be an excellent time for questions if you have. Okay, so this is the martingale, then and take the expectation of f of x minus f of minus x is a p, if you raise it to the 1 over p. Well, I won't raise it. Okay, so what I want to do here is add and subtract the expectation of f. Okay, so I can add and subtract the expectation of f at x ranges over the cube minus x ranges over the cube. So just do it a bit fast. And say that this is p to the p and the expectation of f of x minus expectation of f to the p. Okay. And this is 2 to the p expectation of mn minus 0 to the p. And now we'll apply Markov type. There is this constant t to the p, which is universal. K goes from 1 to n. Expectation of mk minus mk minus 1 to the p. But what is mk minus mk minus 1? What's the conditional expectation? So it's 2 to the p, t to the p. Sum k goes from 1 to n. Here, just write it for what it is. There's an expectation of x1 up to xk in principle. And here I have a conditional expectation over yk to yn. The first thing, which is mk, is f at the point x1 up to xk, yk plus 1 up to yn. And the other one, I have to also average with respect to the kth coordinate. K minus 1, yk up to 1. Okay, I'm just substituting what the Markov is. And now I have here this little expectation over yk. Now yk is going to be equal to xk with probability half and equal to minus xk with probability half. So I'm going to have a factor half, which is going to kill this. Okay, but it doesn't matter too much. I can basically pull out the conditional expectation. So pull out the expectation over all of those things. So the factor half is going to disappear, but it doesn't matter too much. And here I'm going to have an expectation over x and y. And here I'll have f at the point x1 up to xk, yk plus 1 to yn minus f. So the probability that these two are different was this factor half. So what I have now is x1 minus xk, yk plus 1 to yn. Okay, so here, just a bit careful with the constant, but anyway, this is exactly what happens. But what happens now, the difference from what's written here to what's written up there is just dummy variables, right? So I just call the first one x and the other ones y. But this is really exactly what's written up there. Okay, if you switch the x to y. Right, so maybe switch y to x. Okay, what's the proof? So the fact that from martingale type, it was written differently in Krzysztof's paper because he was working with p-smoothness directly, so his proof encoded also the tensorization of PCA in a way. But the fact that martingale type implies M-flow type is just a Jensen inequality here, you pull out conditional expectations. Okay. Are there any questions? Which I guess is also the way one proves the Poincare inequality using the decomposition of the variance as a sum of conditional variances. It's exactly the same proof. Okay, are there any questions on this? So we know how to compute M-flow type because of remark number 2. So remark 2. Implies nonembeddability Hamming graphs in 12 spaces. Because we have computed the martingale type, you'll get an idea how to compute the marginal type over the basis. Okay, so okay, but now we're here. We're still in the 90s. So there's a theoretical gap, right? So M-flow type clearly implied Rademacher type. Martingale type almost clearly implied M-flow type. And in fact, already M-flow in 78 asked how different was M-flow type from Rademacher type. Okay? And a lot of people thought that in the meantime, Bourdieu, Milman, Bolson, Pizdier, Naor, Schechman, Thomas with Naor, they had a paper, I had a paper on this, 2 papers actually. So a lot of people thought about it. It was a major open problem in the field to fill the theoretical gap. Okay? So, and the theorem, due to, is really unhandled. Sasha Holberg in 2020 was that, in fact, one can prove M-flow type from Rademacher. Okay, with constant which is proportional up to a factor of 4 or something, I don't remember, but less than 4. So this theoretically gives a purely metric characterization of Rademacher type. Okay, and this is the kind of characterization that we are seeking a lot in this theory, to have metric properties which are fully equivalent to linear functions. And this is important for some reason that maybe we get to later, but this does answer completely how can I compute the M-flow type of an order. Okay, the answer is you have to compute the Rademacher type up to the value of the constant. Okay, now something else I want to say. Any questions? What? Okay, so let me just go back a bit to do a small homage to this very nice paper of Christoph from 96, because I think more people should read this. So we saw that if a space has Martingale type or Rademacher type, because of this theorem, but okay, Martingale type say P, the distortion to embed the Hamming cube in it is n to the 1 minus 1 over p. But what Christoph asked at the time, which is I think very, very insightful, so is what if we don't just fix the type constant, if you want, but we also fix the dimension? Okay, so of course, I mean, if you fix the dimension, everything has type 2, it's all isomorphic. But then we're going to care a lot about the dependence on the type constant. Okay, so the theorem that Christoph proved, I think that's the main part of that paper from today's point of view, is that then the bi-Lipschitz distortion into x of minus 1, 1 to the n, let's say if b is smaller than n, and that's the interesting case, what happened when the distortion is small, we prove that this can be bounded by n over the p smoothness constant, which is good, that's what we had before too, times d to the 1 over p. Okay, the argument which I sketched for you would have, no, which I proved for you, would have given n to the 1 minus 1 over p divided by the smoothness constant, but actually the theorem is that if the dimension is much smaller, you can win by a lot. And let me tell you what the reason for that is, and that's really a beautiful topological argument using the Bourse-Coulomb theorem. So he proved that if f is a function from minus 1, 1 to the n into x, which is now Rd with some norm, then there exists a subset of the coordinates, which I'm going to label as sort of the important coordinates of cardinality d. There exists a point w of plus minus 1 in the unimportant coordinates, and a product measure which I'm going to denote by mu on the important quantities, such that you have the following inequality. On the left, I'm going to have again the double average, which will be on the important, on the pair, no, single average, sorry, on the important coordinates of f at x comma w minus f at minus x comma minus w to the b that measure x. So I'm still looking at antipodal points, but I just fixed the two facets, the w and the minus w facet, okay? And I'm taking the average not with respect to the uniform measure, but with respect to this measure that was given to me now. So the constant is going to be still like before the smoothness constant of p. And here there's going to be a sum over coordinates which are necessarily important, interesting, you know, this one. And here I'm going to take partial derivatives, but only on the two subtubes that I have. So f of x w minus f at the point where I flip the I coordinate. X, yeah, I don't know how to do this. Dx. And what's written here is only a sum on the W subtube, so I have to also sum over the two tubes, right? So I put a plus minus here and a plus minus here. So just measuring the partial derivatives only in the two subtubes. And now, if you look at the distortion bounds, the way that we would prove the distortion bounds, the lower bound will still be the same. Genuinely antipodal points on the tube. But the upper bound will be different because the only thing which matters is the important variables, right? Which are as many as the cardinality of sigma, which is b. Okay, so the point here is that everything that's in this existential quantifier, first of all, depends on the function, and secondly, it's found using the Morse-Coulomb theorem. So there's a topological aspect, which also explains a bit that this does not fall in the classification of dual formulation of bi-Lipschitz embeddings. So the dual formulation of bi-Lipschitz embeddings that I showed before is really about embeddings into infinite dimensions. Because even if you want to do it about embeddings into a space X, to make the duality argument work, to make sure you have a cone, you're going to be forced to go to LP of X. Okay, so to make this duality argument work, you are forcing yourself into infinite dimensions. So that's why this inequality does not look like the Poincare inequalities that we have there. So it's not something which is true for every function. Given the function, you find the subset, you find the point, you find the choices of sign. Okay. So I'm not going to prove this, even though it's a very, very nice theorem. I will invite you to read Christopher's paper. But let me just make a remark. But there is kind of a sort of a gap now where things stand, right? So the distortion bound n to the 1 minus 1 over p, you can prove it just under assuming Rademacher type, because we know that it's the same as Empfler type. But for this, it was proof kind of used p smoothness. So this is something which I used last year. So this was extended to Rademacher type. Last year. Which involved extending a lot of the arguments that were used in this Rademacher type equals Empfler type actually to the biased cube. So it's really something about the biased cube. So this can be done. Yeah, so I don't think I want to speak about the proof. I just want to say just a few words that somehow even just looking at the even just looking at the Rademacher inequality, which used to be here, the right hand side is a sum over partial derivatives squared, right? And the left hand side, you take powers 2, and the left hand side is really a variance. So this is really kind of a vector valued analog of the Poincare inequality in the cube. And there are some necessary assumptions to have. So one can ask, and we did, and many people did, whether you can play this vector valued game and extend other functional inequalities on the hypercube to vector valued functions. Okay, so there are other extensions recently. So there are extensions to vector valued functions of the influence inequality of Taliban. So, depending on what community you're from, this might be called the L1 and L2 inequality, and also more recently of, again, Taliban's LP Loxopoulos inequality, both of which, this one was substantially more difficult in the sense that it used to be a limitation of the methods in the paper of Ivanishvili, Van Handen, and Volberg was needing to be overcome for that. It was an integrability issue that was actually crucial, some kind of singular integral that was maybe kind of unexpected there, in the sense that we expected two to be duality. So this was in 2 papers with Dario Cordero from Paris, 22, 23. And actually, I mean, so using Poincare, one can get the distortion of the hypercube. Using this kind of inequality, you hope to be able to get something slightly more. And in fact, formally you can. So you get some bounds for not just the hypercube, but the quotients of the hypercube, and not even just quotients by subgroup, just quotients by anything. And formally, these bounds are better than what you get by the Poincare inequality. So in fact, what happens if you just look at the bounds, you have some KKL type phenomena for distortion. So you really, you see some distortions and you win by a lot. Now, there's an embarrassing problem, which is why I'm not advertising this more. I don't have a single example where this thing inside the log is not a constant, but I strongly believe that. So I think that this kind of inequalities, there exists a family of metrics on quotients on the hypercube for which is going to give you a better distortion than what we knew. But somehow we are lacking good examples right now when it comes to this. Okay. Any questions? Good.
Will you talk about this?
No, it's psychedelic.
I think there's a generalization of Lacan's inequality by done in one of the students. Do you remember this?
By sorry?
The first time version of
Alexandros is
Yeah.
L1.
Yeah, this exists. But it's somehow between, it's closer to that, but also not exactly that. So the strengthening of the one, but only for Boolean. So yeah, not clear if it means something in this context, but yeah. Okay, so maybe since we have 7 minutes, the next college chapter is small, so I can just finish it today. That's it. That's what I want to say for the hypercube. So let me just speak briefly about what's called spaces of boundedness. Okay, so here's the definition. So this came out in the context of concentration of measure in the 80s. So let X be a finite metric space. And fix a number p greater than or equal to 1. So the p length of X is the least L, such that the following hold. So I want to be able to find a sequence of partitions of X, starting from the trivial sequence, so up to the, just putting the exponent, P0, P1, Pn, up to the other trivial partition. Okay, so it's a sequence of partitions, and satisfying the following. So, first of all,
So these are refinements.
exactly, yeah. So first of all, each pi refines pi minus 1, which means that every element of pi is contained in some element of pi minus 1. And the key assumption here is this. So there exists, so for every I, there exists a positive number alpha I, such that if you are given two sets, B and C, which are atoms of the I partition, and A is an atom of the I minus first partition, such that both B and C are subset of A, so the image is that here is X, so here is A, an atom of the I minus first partition, and when I go to the ith step, I just partition it further, and B is an atom of that, and C is an atom. Okay? So when I take two atoms B and C like that, then there exists a bijection phi from B to C, such that for every B in B, the distance between B and phi of B is smaller than this number alpha. Okay, so I find a way, and I'm going to show you an example in just a minute, to biject the two. They have to be of the same size, that's a consequence. So there is a bijection which doesn't move a lot. Okay, okay, and then the third condition is what is L? L is just the pth norm of these numbers. Almost done in 3 minutes, half the board, I think. So, to give you a nice exercise, if you want, what is the length of the symmetric group with transposition metric? Say the two length. Someone have a very quick one?
And to the one of them.
So here's an exercise. So the p length of the symmetric group with the transposition metric. I'll just say the two length. Is again to the 1/2. Why is that? How are you going to partition a symmetric group? You're going to say, well, at the first step, I'm going to partition on n sets depending on where does my permutation send the value 1. Okay, and then that's my first partition. And the second partition, I'm going to partition further depending on where I send the value 2. Okay. And if I have an atom of the ith partition, comparing it with the I minus first, it just means that two permutations agree on the first I minus 1 elements, and you just want to find a way to pass from one to the other. What are you going to do? Just do one more transposition. Right? So, okay, so there's this notion of a length of a metric space, but it can be computed. Okay, this was I should say this fact was used by Moret in the 70s for concentration in the symmetric group. And here's the theorem that I won't prove, but close with this. Due to Otto R from 06, we prove that if Y is smooth, and X is a finite metric space, then the distortion required to embed X into Y is bounded below by 1 over the smoothness constant of Y times the length of Y, sorry, the length of X, and then a quantity which we encountered before in the case of expanders, which is the average distance between 2 points. Okay, just in the really last minute, this is also an exercise. I mean, your partition gives you a martingale, so it's not actually the moment you phrase in the right context and you consider the martingale given by the partition, actually going to say that the proof just works out. So, for instance, if Y has martingale type 2, then, and you apply this thing for X being the symmetric group, then any function from the symmetric group into Y satisfies a Poincaré-type inequality. So you have on the left the expected distance between F at a permutation and F at an independent permutation, as the norm of Y. So this is bounded above by 2 smoothness constant squared, martingale type constant, divided by n minus 1. See, here I'm going to sum over transpositions. And I'm going to have the expectation F at tau pi. And if you just apply this inequality, you get, for instance, that the Euclidean distortion of the symmetric group with the transposition metric is at least square root of n. This is short. So you can get a lower bound for the distortion of the symmetric group based on martingale type, and you saw that for the case of the Hamming cube, going from martingale type to Rademacher type was actually a massive open problem, open for a very long time. And the Hamming cube itself has this structure of independent random variables in it, right? So one can ask, is it possible to go from martingale type to Rademacher type to this inequality? And Mira Gordian is going to tell us about this on Friday. There's a really exciting inequality for Rademacher. And yeah, that's it. Sorry for being a bit over time. Thank you. Question?
Is this really C2 of Sn?
Yeah. So, and the embedding is not this complicated. So, I think you just look at the permutation matrix, and so you map the permutation to the permutation matrix, and maybe this incurs distortion over time, I think.
It makes sense.
Maybe I'm, yeah, don't quote. But they've written the embedding on their paper. I think that this is it. Yeah. So it's really squared.
Any questions? I have a question. What kind of distance is that?
Here?
No, there. At the top.
Here? Okay, good. So you take the symmetric group and you take the generating set, which is all transpositions. So all permutations that swap 2 elements. So you say
how many transpositions?
exactly how many transpositions do you need to go from one, which is arguably the most important. People care about many metrics in the symmetric group.
Even diameter is not totally trivial.
I choose to.
What?
I choose to.
The diameter is,
The diameter,
yeah,
it's just
it's
And minus
more
one.
than,
minus one.
Because you
You
find
can
the cycle
decompose that
structure.
permutation into transposition.
In case cycle is given
Oh,
some transpositions.
This we can. Okay, good.
Any other questions?
Tomorrow morning.